This is part one in a two-part short summary of solution chemistry. It's important, first of all, to start out reviewing the types of compounds or molecules that are out there. The first type that you should be familiar with is ionic. Ionic over here is going to be our metal and nonmetal. In other words, it's going to be a positively charged ion bonded to a negatively charged ion. Okay, so the type of bond here is an ionic bond. And it's like a magnet. It's the same reason that two magnets stick together. It's the attraction between two opposite charges. You have to remember that opposites attract. Now, usually when we draw bonds, we're going to draw a line in between two atoms. But with ionic compounds, you cannot draw a line in between. Ionic compounds are simply just written like this. They're written close together. We can represent them with a plus or a minus, although when they're combined into a compound, they are neutral. Looking over here at covalent compounds are going to be generally two nonmetals. Okay, they are not really going to be charged, so we can't draw a plus and a minus necessarily. The way that they're bonded together is through a covalent bond. Now this is more what you're used to seeing in chemistry, where we see lines in between our atoms that represent bonds. Each line represents shared electrons. Okay, each line here is a pair of electrons that are shared. Okay, but the problem is that not all atoms are going to share those electrons equally, which is why we have two different kinds of molecular compounds or covalent molecules. The first kind is going to be polar. This is when they are not shared equally. And over here we have nonpolar. This is when they are shared equally. Okay. Now, sharing equally or sharing unequally is based on that particular atom's electronegativity. Electronegativity refers to that atom's ability to attract these shared electrons to them. In fact, a lot of times these shared electrons are not going to be directly in the middle of two atoms like it is drawn. Okay? When they're not directly in between, we say that it's polar. An example of a polar molecule, as you should know by now, is water. Because our oxygen is more electronegative than our hydrogens, I'll say that again, the oxygen is more electronegative than the hydrogens, those electrons are actually spending more time up here near the oxygen. We know that electrons are negative, therefore, we say that our oxygen is partially negatively charged. Okay, it's not over here like our ionic bonds where it's a full negative or full positive ion. Here we just say that they're partially charged. If they were full ions, it would be an ionic compound, but it's not. Okay, over here we have our nonpolar. This, for example, would be like a diatomic molecule of fluorine. Because fluorine is going to have the same electronegativity as another fluorine, they're going to share those equally, and in fact those electrons are, for the most part, going to be right in the middle. Okay, so other examples of polar molecules are going to be sugars, I should say, because there's different types of sugars, as you should have learned in biology. We have sugars and, for example, alcohols. Okay, other nonpolar substances, we can think of oils. Okay, let's talk for a moment then about what does this have to do with solutions. Before we can do that, we need to look at some basic properties of solutions. Let's move this up. Okay, basic properties of solutions is that solutions are made up of two parts. Now, I like to use Kool-Aid as an example. So here we have our packet of sugar. We have our packet of sugar, and we're going to add it to our pitcher of water. When we do that, we get, you know what, I should have drawn this. Although blue Kool-Aid is pretty good, I could have used blue. Here we have our clear water. And in the end, we have our Kool-Aid. Now, in terms of vocabulary for solutions, in this case, because the sugar is the thing that's being dissolved, okay, the sugar is the thing that's being dissolved, so we call it our solute. Our water, in this case, is doing the dissolving, so we call it our solvent. And our final product is going to be, of course, our solution. Okay, so the two parts of a solution are the solute and the solvent. All right, so let's talk about how ionic compounds and covalent compounds behave in solutions. So let's go ahead and make a T-chart. So over here we have our ionic compounds, which is our cations and anions bonded together through ionic bonding. And over here we have our covalent. Let's not forget that we have two types, polar, which has regions of opposite charges, and nonpolar, which is essentially, we can consider it neutral. Okay. Over here, when we talk about ionic compounds, we're mostly talking about aqueous solutions. Aqueous solutions just means that it's dissolved in water. Okay, so just like our Kool-Aid, our solvent here is going to be water, always. So there are going to be two types of salts. A salt is just a generic term that we can use to describe an ionic compound. There's going to be two types. There's going to be soluble, which means it dissolves, and insoluble. That's kind of sloppy. And insoluble, which means that it does not dissolve. So for example, we have magnesium chloride, which we know does dissolve. So what we end up with, and this should be 2+ charge here, but I ran out of space, and our Cl's over here are -1. It's kind of sloppy, I apologize. But basically what you should notice is that it's going to break up into solutions. So this Mg is going to come apart from each of the two Cl's, and the two Cl's are going to come apart from each other. And what you'll end up with is a bunch of ions that are floating around in your water. Okay, they're going to be dissolved by the water, and we'll talk specifically about how that happens in the second video. When we have an insoluble salt, such as, we'll say, silver chloride, nothing's going to happen. You're going to put it into water, and it's going to stay a solid. So we would call that one a solid, and we would consider this one to be aqueous. When we form a solid through a reaction, it's called a precipitation reaction, and the solid that's formed is the precipitate. Okay? So precipitate is the product of a reaction that forms an insoluble salt. Okay, let's look at covalent compounds in terms of solutions. We have this saying in chemistry, and it says like dissolves like. What that means is that polar dissolves polar. In other words, polar solvents will dissolve polar solutes, and non-polar solvents dissolve only non-polar solutes. This is why if we put oil and water together in a beaker, we'll get a layer of oil and a layer of H2O. They do not mix. They're immiscible. They do not mix. They do not dissolve each other. And this is because they're not attracted to each other. Basically, the water is going to be more attracted to other water molecules through hydrogen bonding. Okay, this is what's happening in this bottom section. It's going to be more attracted to each other than it is the oil. Now, a lot of oils are going to have a bunch of C's and H's in different quantities. We'll just put generically C's and H's there. There's no charges here. There's no positives or negatives, there's no attraction whatsoever. So the water is going to say, okay, I'm gonna stick to my own kind here. I'm gonna bond to myself, and I'm not gonna worry about the oil. All right. So what I want to do then is I want to talk about something. Let me move this up here. I want to talk about something called electrolytes. Electrolytes versus non-electrolytes. We'll put that in a different color here. Versus non-electrolytes. Generally speaking, electrolytes are going to be our ionic compounds. Ionic compounds. Our non-electrolytes are generally going to be polar covalent compounds. Okay, so both of these are going to dissolve in water. Both of these dissolve in water. But there's one really, really huge difference between them. And here it is. My beautiful beaker drawings. Okay. Ionic compounds, such as we'll use sodium chloride, which is kind of a classic example when we're talking about ionic compounds. Sodium chloride is going to go into this beaker as a crystal structure, and it's going to get torn apart by these water molecules, and what we're left with are a whole bunch of ions in the ratio, of course, 1 to 1, because for every 1 sodium, there's 1 chlorine. Okay, we don't see any subscripts, so we assume that it's kind of an invisible 1 as a subscript. So here they're going to break apart into ions. They're going to break up into ions. Over here, polar covalent, we'll use sugar for an example. We'll use sucrose. Okay, sucrose is C12H22O11. Now this will dissolve in water. In other words, if we put a whole bunch of sugar in here, it will dissolve. It will be surrounded by water molecules. The difference is that here, with our ionic compound, our sodium and our chloride broke apart into ions. Here, we're going to be left with our sugar molecules intact. In other words, they did not get ripped apart. They're unchanged. Okay? So because of this, over here you'll notice that we have, that's supposed to be a star, that we have positive and negative charges. Over here, we don't have any charges. Of course, we know that since it's a polar covalent bond that we're going to have some partial charges involved, but not the kind of charges that are required to make it what is called an electrolyte. So electrolytes break up into ions, and they're going to be able to conduct electricity. In other words, if we put 2 electrodes into this solution, it'll be able to complete the circuit to, for example, light a light bulb. Okay, that's where we get the name from, electrolytes, electricity. When it breaks up into ions, it conducts electricity. Over here, since we have no real charges, these guys are not going to conduct electricity. Electricity, which is why we call it a non-electrolyte. All right. Finally, last thing I want to talk about here is I want to talk about very, very briefly 3 different types of solutions. We want to classify them based on how much solute is dissolved in the solvent. Okay, so the first one is going to be an unsaturated solution. Second one, saturated. And the third one is supersaturated. Okay, unsaturated solutions contain less than, okay, that's a less than sign, less than the maximum maximum solute that will dissolve. Okay, so we can still fit extra salt or whatever we're trying to dissolve in there. Okay, we can still fit some extra Kool-Aid sugar in there and it'll continue to dissolve. Okay, there's still some extra space. Saturated, however, has reached its max. Reached its maximum amount of solute. So if we're using Kool-Aid, for example, this would be like adding a whole nother packet into your pitcher of Kool-Aid and still ending up with a whole bunch of solid pieces that just do not dissolve, okay, because you've reached its max. So as soon as you've poured enough solute that can possibly dissolve, it's considered saturated. Now, supersaturated is kind of a complicated process, but basically, supersaturated, you're going to saturate it at a high temperature, cool it down, and you're going to add what's called a seed crystal, which is basically a particle that's going to form crystals in your solution. Okay. You're going to form crystals. And this is because it has reached its max at a high temperature, you cool it down, and suddenly some of the solute comes out of solution as a precipitate. Okay, and that precipitate we call a crystal. So if we were going to draw this as a representation, we could draw our beaker here. Of course, this is actually dissolved, so you're not going to see the actual particles. But here we would just have a little bit of solute relative to this one, where we would have much more. And then, of course, supersaturated, we said that we're going to be forming crystals, which will kind of look like solid pieces. Great drawing, right? These are crystals. So anytime you see the word crystals or crystallize, you know that you're dealing with a supersaturated solution. Anytime you see that our solution has reached the max amount of solute, it's saturated. And finally, unsaturated, you can still fit more. So in the analogy of a restaurant, an unsaturated solution is a restaurant that still has some tables available. Saturated, it's reached its maximum capacity. We're now on a wait list. The restaurant cannot hold anymore. And a supersaturated is when some people are actually kicked out of the restaurant because the restaurant just cannot hold any more people. Being kicked out of the restaurant represents the crystallization or the precipitation of this solute coming out of solution. Okay, in the second part of this video, or rather part 2, we're going to talk about the actual microscopic level of dissolution of salts, and we're going to talk about factors that can actually affect how fast a salt is going to dissolve in water. Okay.